Hello, my name is Eric Zoerner and I work for eBuddy. And what I'm going to talk about today is an open source Java library that sits on top of the driver layer in Java as support for your applications to denormalize your data by writing structured objects to Cassandra. What I'm going to talk about, I'll mention briefly who eBuddy is and what we do, and then I'll introduce the library, which I call Seastar Path, and go into the details of how does it work, how is it designed, and what were some of the challenges in implementing it, and go into the details of how the data is modeled in Cassandra using this library, and then finally some plans for the future of what I'd like to do or what we would like to do with the library. Okay, eBuddy. Some of you may have heard about eBuddy, I don't know. It is what we do is messaging, internet messaging. And the company started with a product that allowed you to connect to third-party instant messaging networks like Facebook and Google and Yahoo and MSN using your smartphone and also a web interface. And we, since then, have developed a second platform, second product, which is a messaging network of our own, which is connects with internet, smartphones on the internet, and also a web interface, but with our own chat network, and it's designed to be a replacement for SMS texting over the internet. And it's called XMS, and it has a number of interesting features which I won't go into a lot of detail about. I'll mention a couple things briefly and how that relates to how we use Cassandra. Because we use Cassandra as the primary data store at eBuddy for our XMS platform. We also use MySQL for some features, but the primary data storage is Cassandra, which we use for a number of features, including user data service. So tracking information about users, like their name, their PIN codes, things like that. And user discovery service. The messaging platform that we have is based on contacts, a contact list. So every user has a contact list of where they can start to, where they can go to start to start a conversation with their buddy, their friend. And we have a discovery service that uses various social graphs. For example, Facebook friends, your address book, Google contacts. It can use several different third-party social graphs to discover other XMS users that are in that social graph. And we use the Cassandra as the database for storing social graphs that our discovery service uses. Also, we use it for persistent session store. This is a user session when they're both when they're connected and when they're not connected. So every user has a persistent session. So once you've connected for the first time, you're always quote unquote logged in. The only difference is whether you're currently connected or not. And we use the session for a number of things like caching the contact list and various pieces of data that we need to track the users. And we use Cassandra to store those user sessions. We also use it for message history. So when you connect with a client, depending on, there may be some state on the client or there may not be, but the client can query XMS to get the message history for its conversations, and we store all the message history in Cassandra as well. And we also use it for location-based discovery so that you can find other contacts, XMS contacts that are nearby. And we do that through geo-hashing. And so when that feature is enabled, we store locations in Cassandra, and then we use that for looking up other users based on location. And just to give you an idea of our data, we have about half a terabyte of actual data, which is replicated. 16 million sessions approximately right now, which includes both sessions for users as well as for group conversations also have their own session. And we have one particular column family, which is kind of an index into other column families, which has almost 1 billion rows in it. But what I want to focus on in this talk is the library, Seastar Path, which we have recently open sourced, because I think it's a useful library to help in Cassandra applications to store structured data in Cassandra. So it addresses a classic problem, is that I have complex objects, complex structures that might contain collections of other objects, and how do I store that in a data store that supports simple data like keys and values. For example, a relational database has columns and value cells, and also NoSQL databases such as Cassandra, a key value store. So that's a problem that there's been many different solutions to. For example, you could serialize your data. So you take the whole complex object, convert it into bytes, one way or the other, store those bytes in the value of a key value in a cell. It could be binary, or it could be textual. For example, XML. You could convert your object into an XML structure and just save that. So that's a very popular way to do it. Or you could normalize your data by breaking it up into separate tables and then have connections, relations from one table to another using IDs. That's another popular solution to this problem. Another way that you could do it is to decompose your object into paths, which is the solution that we decided to go with for this library. So it's one solution out of many, and basically what it is you just break down your object into paths, kind of like you might do with XML and XPath, for example. They're just navigation paths into the objects to reach the simple values like the strings, numbers, Boolean values. So complex data is made up of in the end, it's like a graph, and the leaves, the terminal nodes of this graph are just simple values. So each solution has advantages and disadvantages. Serialization has the advantage that you can do a single write. When you write the object to your database, you package it up into a blob, and you just do one write, and the whole thing is there. You can read it back with a single read. So these are advantages, especially with Cassandra. I think you probably have all heard about best practices with Cassandra is to denormalize your data so that you can read and write your data with one write or with one read to hit a single partition, right? A single row, single node. So serialization can offer these benefits. And it also can be a pretty good guarantee of a consistent update. So you're reading and writing an entire structured object in one go. It's not easy to get a partial read or to corrupt that object with a partial write. So it gives a good guarantee of a consistent update. So you're either writing the whole object or nothing, right? Structural access. What I mean by that is the ability to access parts of the structure. So a single street name, a single address from a more complex structure. So serialization doesn't really allow you to do that. It's all or nothing. So it's kind of the inverse of consistent updates there. Also, cycles. If you have data that is self-referencing, it is possible to serialize it in such a way that you maintain these cyclical references, right? And so that you can maintain those cyclical references when you read the object back out again, depending on how you serialize it. So that is a possibility with serialization. Normalization, you split the object into multiple tables, so you lose the ability to update the structure with a single write or a single read. So this is the main reason why normalization is not a best practice with Cassandra. It's better to denormalize it. And normalization can give you some surety that you're doing consistent updates, but perhaps not. That's a little bit iffy. It depends on how you do it. It would be possible to do inconsistent updates, but if you're talking about this in reference to like a relational database, of course the database provides ways to have the database enforce certain kinds of consistent updates. So yes, in some cases it's possible. Structural access, yes, you can read and write parts of the object just by reading and writing to a particular table. And cycles, yes, you can also model cycles with normalization because you can have links, use identifiers to maintain object identity, right? With decomposition, you also get the benefits, a lot of the same benefits of serialization with single writes and single reads, which is why I think it's good for Cassandra use. We'll talk more about consistent updates. It's not really enforced by the library. The library remains flexible, so it is possible for an application to shoot themselves in the foot with an update that doesn't make sense. But it does allow for structural access. You can get at any piece of data that you want. You can read or write at any level of the structure. And cycles is more difficult with decomposition because there's no identifiers to maintain object identity. So there's some trade-offs. Seastar Path is an implementation of object decomposition, which has recently been open sourced. It's available on GitHub at this path, at this address. And the artifacts are also uploaded to Maven Central. So it's a library for decomposing complex objects into path value pairs and storing them in Cassandra. So I think some plus points on this library is that it's very easy to use, very simple API. And it's good for Cassandra, I think, because it provides structural access. You can read and write, you can write parts of the object without having to read the whole object first. So that's a best practice with Cassandra. Good for denormalizing the data, so you can read or write large complex objects with one read or write to like a single row. And so let's look a little bit more closely at how does it work exactly. First we'll look at some API examples. So the main interface in this library is called Structured Data Support. It is intended to be a layer above the client driver, but a layer below your own application data access layer. So typically you would write your own data access objects that speak the language of your application domain, and you can use a data support object to help your data access object to read and write to Cassandra. So in this API example, I call the structured data object, or the structured data support object DAO, just because it's short. It fits on the slide better, but it's actually more of a DAO support object. It isn't actually intended to be a DAO object, although you could use that for simple cases as a DAO. So given a row key and a POJO, which is an object in your application domain, you specify a path of where do you want to store this object. Where do you want to write it? So you just create a path using this support object and specify the elements in the path. So X, Y, Z. You can make it as long or short as you like. And then with that path, you just call write to path and give it the row key, the path, and your POJO. And it does the right thing with a little bit of help, perhaps. And we'll dive into that a little bit. To read an object from a path, you again create a path, and then you say read from path. Give it a row key, the path, and a type reference. So this tells the library how are we going to recompose this object into your POJO. So if you're familiar with Jackson library for doing JSON, then this should be very familiar to you. It isn't the JSON class, but it's pretty much a copy of it. It's based on the JSON implementation, where you basically say the object I want is of type POJO, and the reason you have to use this strange syntax has to do with the idiosyncrasies of Java generics and type erasing or whatever. So the generic type becomes available to the library at runtime by using this mechanism. The generic type can be as simple or as complex as you need it to be. So it can be a nested generic as deeply as you need it to be, and the library will be able then to reconstruct the object using your POJO types exactly as specified, assuming the data is consistent. To delete, you just say delete path, give it a row key and a path. So very simple API. It also supports batch operations. The library comes with an interface called batch context, which is an abstraction so that the library can be used for multiple implementations. There's actually a CQL implementation and a Thrift implementation in the library. So batch context is just an abstraction. So this code, you write to this API and it will work with either CQL or Thrift with no code changes. So you just create a batch context from the DAO support object. And when you do your writes and your deletes, any mutating operation, you just pass in that batch context. And then when you're ready to apply the batch, you just call apply batch on the DAO support object. So you can read or write an object at any level. So say you're writing a person object and you're writing it at path X. You would write to path and then you could then read just the name of that person by you concatenate the name element to the path X, so you get the path X/ or X name, and then just read from that path, and then you just get the name of that person. So you can do that at any level. So now let's look a little bit at the implementation. So to decompose an object, a structured object, the first thing it does is it converts that domain object into a basic structure of maps, lists, and simple values like strings, booleans, and numbers. And to do this, it actually uses the Jackson library. So an advantage of using the Jackson library is that not only do I not have to write it myself, it also means that it will honor the Jackson annotations on your domain objects. So you may already have Jackson annotations on your domain objects for converting those objects into JSON, right? So the same annotations are honored in this library for converting your objects, breaking it down into basic structures, maps, lists, and simple values. And then once it's done that, it will take that basic structure and decompose that into a map of paths to simple values. And this is done by an object in the implementation called the decomposer. So it basically walks the object and creates a map of paths to simple values. And then it writes this map to the database. Example, so you take a complex object like a person with addresses and phone numbers, and then it simplifies it into maps, lists, and simple values. So you get a map, name, John, birth date, nickname, a list of addresses, and a list of phone numbers. And the addresses are also broken down into a list of maps. So objects become maps, and collections become lists. And then it creates a map of paths mapping to simple objects like strings and numbers, etc. To read, we basically read the paths and values out of the database at a given path, which means if you specify, for example here, if you specify the path addresses, then it will do a slice query to get all the paths that begin with the element addresses. So it gets all the structure underneath as well. Reads path values from the database. Okay, and then it takes those paths and values and merges them back into the basic structure of maps, lists, and simple values by an object called composer. So we have decomposer and composer. And then it passes this basic structure back to Jackson and gives it a Jackson type reference and says, give me your Pojo back. So yeah, that's leverages the Jackson library to do that. So design and challenges, some things that are more specific to use with Cassandra. So the paths themselves are stored as strings. You saw that there were forward slashes in the paths. That's hidden by the Path API. It was a design decision to store them as strings. There is another option that I'll talk about in a little bit later that we decided not to do, at least not yet. The path elements are internally URL encoded so that we can use some special characters that are used internally by the library. For example, the @ symbol is used for list indexes, index into a list. The Path API also, by the way, allows you to specify a list index in your path. So it is possible to read and write to individual list elements using the library. A challenge is shrinking lists. Okay. The shrinking list challenge. You write a list to the database, for example, 1, 2. It ends up in the database as if you say you start with the path X, X at 0 is 1, X at 1 is 2. And now you write a shorter list at the same path. So now you write the list 3 to the same path X. The 3 overwrites X at 0. Okay. So that's kind of a problem because now if I read from the path and say I want a list of strings back, I get 3, 2, which is not, nobody ever wrote a list that was 3, 2. What happened was the list shrunk on this right, and it left behind an element from the longer list. It's still there in the database. So how do we fix that problem? Well, the implementation writes a ListTerminator column. So when you write 1, 2, it writes a special terminator at 1, 2, sorry, at 0 is 1, 1 is 2, and it writes an extra element, which is a special terminator. Yes, so the values here, as we'll see later, the values here are also always typed as text. So I used a special text value here, which is an illegal Unicode string, well, reserved Unicode string, to indicate that it's the terminator. And then if you write the 3 back, it'll write the terminator at 1. And then you read the whole list back, you get the right answer. Okay? Well, that's, unfortunately, it's only a partial solution because it's still possible to read stale list elements using a positional index in the list. So if you specify a list index, it's possible to get back a stale list element that was not intended to have been left behind by someone doing a write. You can avoid that if the client, if the caller, knows that that could happen, and so it could do a delete before it does the write. Okay, well, yeah, the library does not enforce that. But so it's up to the client to do the right thing. So it's also up to the client, the user, to know what they're doing and understand something about how this is implemented, right? So the shrinking list problem, it's been solved if you are reading and writing entire lists at a time. But if you're going to do reads of individual list elements, then there's still a caveat there. Another challenge, inconsistent updates. So because an object can be updated at any path, there's no protection against a write corrupting the object structure. Yeah, so say you write at X a person. It writes the address and name at these paths. And then you write the same person, say, at X name. Okay, so now in your database, you have X address street, X name, which contains a string. But then also at X name, you have more structure. So you have both a simple value and structured data at the same path. So that is not consistent, right? You cannot have a simple value and a structured value at the same path. But it is possible to store it that way in the database. So the solution is don't do that. Okay. The user of the library needs to know what they're doing because it is possible to corrupt the data if you do something wrong, right? The library does have a way for the data to be retrieved even if it's corrupted. It has a way of resolving that conflict with a special root object. So it's possible to get the data out again if that happens. However, if you try to convert that data back to your POJO, that will fail because the data is no longer consistent with your POJO structure. Sorting. What about sorting path elements as something other than strings? Say you want a path element to be numerical or time-based. Perhaps you store it in a sorted map or something, and you want the data to come out in the right order. Well, instead of storing the paths as strings, an implementation decision could have been to use dynamic composite keys. That way, each path element can have its own data type, and at each level can be sorted according to that data type. We tried that. Yeah, we did try that. I tried that, and it can work. I did get it to work. Even with CQL, it works because dynamic composites are considered to be user-defined types in CQL. And CQL does support user-defined types. However, if you try to look at the data with dynamic composites, it causes CQL shell to crash. And in general, it's not as nice to be able to browse the data. So at least with this version of the library, we decided to just keep it simple and use strings. When you read the data back into your POJO, if your POJO is a sorted map, those keys will naturally get resorted on the client, right? But for this version of the library anyway, we always store the columns as strings, so they will always be sorted in the database as strings. So still considering doing dynamic composites in a future version. So that's a possible future. Yeah, starting to run out of time already. I want to take a look at the Cassandra data model in Thrift. We just store the paths as column names and the values as values, as in column families. With super column families, it's also possible, well, possible in the sense that it's not implemented yet, but it is planned. The first element of the path will just become the super column name, and then we'll go from there down for the rest of the path. The Thrift implementation uses the Hector client, and to create a Thrift structured data support object, you give it a template object that's also part of this library. It's our own template object that does all the basic operations using Thrift, using the Hector client. So it's kind of an abstraction. Well, it is an abstraction on top of the Hector client, which is in turn an abstraction on top of Thrift. So you create a template, give it the Hector serializers that you need, and the structure serializer is part of the library as well, and that's just used to be able to actually it uses serialization if you actually were, well, that's implementation detail, but it encodes structured objects if you were to write those as well. So it's possible to use this library also to write structured objects directly instead of decomposing them first. And then it just serializes them into JSON, basically, and writes them as JSON. And then CQL, there's some constraints on the data model. you can use it with any table, but you have to have the path itself is a column, and we use a dynamic column family for this. We cannot use the path itself as a column name in CQL because it's dynamic, right? It's not fixed. So we use a fixed column name, like for example, path. Key is the partition key, such as path, and then another column called value. So we store it as key value paths, column or path values in the table. So you would have to set up your table in this way and give it the key and the path as the primary key. Key is just the row key, the partition key, and the path has to be a clustering key. And the reason for that is we're doing range queries. The library does range queries on that path column. It needs to do a range or slice query on the path, so the path must be a clustering key. It has to be the first clustering key, because otherwise we'd have to use an equals condition on the previous clustering keys in order to do the query. This is basically the constraints on what kinds of queries are possible to do with CQL. You might think that you could just put a secondary index on the path column instead of making it a clustering key, but that doesn't quite work either because Cassandra indexes really only work with equals conditions. If you try to do a range query on a secondary indexed column, then you get an error like no index columns present in by columns clause with equal operator. So they also only work with equals. And the CQL implementation uses the DataStax Java driver. And when you create your CQL structured data support object, you give it the table name and the path and value column names, where the partition key is, and a session. And then it uses that session for all of the querying. And then finally, things that are planned for the future, sets with simple values. This is very similar to how CQL would actually nest sets as well. And CQL also currently only supports simple values because if it's a set of complex objects, then it's not really possible to maintain the structural access of those objects. So what I'd like to do is with sets of simple values is to be able to put those simple values into the column names, into the key part, and then that way you can do set operations, access, do contains, access elements of that set individually. Dynamic composites is a possibility. Also, the API, I believe, should support multiple rows, like a multi-get, and multiple row reads and writes, and slice queries on path ranges, so not just a single path, but a range of paths. The API can also support that. So this is where the library is located on GitHub, and I'd like to open it up for questions.
Actually, if I may interrupt, the lightning talks and the ending session are starting in about 2 minutes.
Okay.
In the auditorium. There is supposedly still seating